and a mysterious visitor is on its way to Earth, moving closer.
There's a mysterious interstellar object hurtling towards our solar system, exciting scientists across the globe.
It began, as many of science's turning points do, not with a burst of fanfare, but a silent moment overlooked, hidden in the patient archives of a digital sky. There, layered across thousands of pixels and stored away from immediate eyes, awaited a secret. Most attention was on distant planets orbiting other suns, on ancient stars carving new histories, not on what might be happening in the dark between them. Yet, drifting quietly onto the vast cosmic canvas, arrived a visitor unlike anything native to our sun's realm. This visitor would become 3I/ATLAS, the universe's third confirmed interstellar object to pass through our solar system. It joined a list so short and so extraordinary that every new member turns the astronomical world on its head. But its story, as discovery tales so often do, didn't conform to the clean lines of first contact. Instead, its presence was revealed piecemeal, the clues scattered across time and technology. When official discovery came in July 2025, the headlines were immediate. News outlets and astronomers alike proclaimed the arrival of a true outsider, a body not born within the solar system's own chaotic nursery, but flung across interstellar distances. Yet as celebrations rose, so too did subtle doubts and questions. Had anyone already glimpsed it before, that July marker? Was there evidence hidden in older data, captured by other eyes, overlooked at the time? What ensued was a quiet revolution in how we define first sight. At its center was an unexpected protagonist, not Atlas, the observatory that announced the discovery, but TESS, the transiting exoplanet survey satellite. It was designed to watch for the faint dimming of stars as planets pass in front, not to survey for rogue interstellar bodies. Still, as researchers delved into TESS's massive data archives, they found evidence that 3I/Atlas passed through its view as early as May 7, 2025, 2 months before ATLAS sounded the cosmic alert. This realization didn't just rewrite the timing of discovery, it cast new light on how science itself works, showing that breakthroughs may wait in old data, revealed only when curiosity asks the right question. A visitor from beyond. It starts with a motion, nearly invisible, a faint smear or point among the starlit sky. The official record notes 3I/ATLAS was first spotted by the ATLAS telescope in Chile on July 1, 2025, some 670 million kilometers from the Sun, little more than a shimmer at the limits of detection. The context makes this event exceptional. To date, only 3 interstellar objects, Oumuamua, Borisov, and now 3I/ATLAS, are confirmed to have entered and exited the solar system. Each arrival kindles fresh questions and speculation about the chaotic mechanics of star systems, the nature of planetary birth, and the remarkable odds that let any small object drift untethered through the galaxy, only to cross paths with the Sun. The orbit of 3I/ATLAS doesn't reflect our solar system's choreography. Its path is steeply inclined and retrograde, moving against the prevailing streams of local celestial traffic, evidence it's not a native, but a visitor, flung by unknown prior events. This trajectory confirms its origin from far beyond the Sun's own sphere of influence. But the story deepened when astronomers scrutinized TESS data to see what else it may have glimpsed. Unbeknownst to the world at the time, TESS had quietly observed the earliest approach of 3I/Atlas in May and during a second observing period, collecting images and measurements that entered digital archives before anyone knew to care about them. Not only was the interstellar object seen earlier than thought, but its presence in those images was only apparent later, after astronomers retraced its orbital path. This raises a key point. Scientific discovery often involves interpretation and context, not just initial observation. The data's meaning emerged with hindsight, illustrating how readiness and method shape what becomes visible in the ever-growing archives of space science. If you want to keep uncovering these hidden cosmic stories as they unfold, make sure to subscribe so you don't miss the next chapter. Now let's move on. The Forgotten Eye. TESS was not built to search for stray comets from other star systems. Its mission, to find exoplanets by measuring starlight dips across broad swathes of the sky, means it quietly records countless images, most never inspected for moving objects not connected to its main science goal. Yet this vast accumulation of calibrated sky surveys turned out to be a wellspring for uncovering the pre-discovery tracks of 3I/Atlas. Between May 7th and the official July announcement, TESS captured traces of 3I/Atlas as it drifted through its field of view. First, as a faint shift among the stars, its motion making it stand out only when researchers retroactively overlaid the known orbit. The object's brightness and movement weren't particularly dramatic or unique at the time, as the comet had not yet neared the Sun enough to trigger obvious activity. But within the archives, left untouched for months, the silent visitor appeared as a blip that only grew meaningful once its journey was mapped. Rather than serendipity alone, this repeated independent detection by TESS across two observing spans hints at a pattern within astronomical records, that large-scale surveys, sometimes designed for unrelated missions, routinely amass data that could contain the earliest signs of rare cosmic events. Identifying these requires imagination and persistence. This calls scientists to re-examine the unintended treasures stored by our instruments. The discovery of 3I/ATLAS's earlier presence shows that even the most advanced observatories might miss epochal events, not for lack of observation, but because new questions hadn't yet been asked. Activity in the darkness. Perhaps most surprising was the nature of 3I/ATLAS's behavior during those earliest observations. Comets, whether native or interstellar, typically become active, developing comas or tails as they are warmed by the sun's energy. With solar system comets, this activation is usually observed as they draw closer, their ices beginning to sublimate. Yet TESS data demonstrates that 3I/ATLAS was already active as early as May, before its official discovery and before it had reached the region where most comets begin to show such behavior. The spacecraft's images and measurements documented real changes. The object was not simply a cold, dormant remnant, but emitting gas and dust, displaying a level of cometary activity that stood out once its path and properties were studied. These early signs offer insight into both its composition and its journey. Interstellar comets, like 3I/ATLAS, may have experienced a different history from native comets, possibly spending eons exposed to cosmic rays and extreme environments, or originating from a system with different chemistry. The early activity noted in the TESS data could mean its surface and ices are more prone to outgassing at greater distances, or that it contains more volatile materials, although exact details are still under investigation. Regardless, TESS's continuous sensitive gaze enabled the first chapter of this awakening to be documented, making clear that our encounter with 3I/ATLAS was not a simple story of first contact. The active comet was already journeying inward, changing as it went, for weeks before the alarms were raised. Layers of inquiry. As the community absorbed the new timeline, observatories worldwide rushed to schedule new observations, hoping to capture further details before 3I/ATLAS sped on its way. While backyard astronomers added their contributions, it was TESS that supplied the prologue, changing the narrative of how discovery unfolds in the data age. This episode emphasizes an enduring lesson. Scientific breakthroughs can hinge on retroactive analysis, re-examining archived data in search of hints missed during real-time review. It is not only about building new instruments or stretching the limits of sensitivity, it is equally about returning to existing records with updated models and new hypotheses, seeking signals whose importance could not be recognized previously. 3. I/ATLAS's journey into awareness was marked first by TESS quietly and then by ATLAS with international attention. The aftershocks of this realization have shifted priorities around the preservation, accessibility, and examination of space archives. Each new look backward can alter the course of inquiry, making yesterday's routine exposures the foundation for tomorrow's surprises. If you find these complexities of the cosmos compelling, remember, ongoing discoveries often begin in places already passed by, waiting for new perspectives. Unmasking the Messenger. While TESS's early data forced a revision of the discovery record, another powerhouse of modern astronomy brought its full capabilities to bear. The James Webb Space Telescope, JWST, with its unparalleled sensitivity at infrared wavelengths, observed 3I/ATLAS on August 6, 2025, using its near-infrared spectrograph. Here, for the first time, astronomers were able to analyze the object with exquisite detail, breaking its light into spectra that chart molecular composition and structure. JWST's readings complemented the wide-field visual images of TESS and the discoverer's first reports. Webb's spectral data allowed scientists to search for telltale signatures of familiar cometary ices, such as water, carbon dioxide, and carbon monoxide, and to look for any anomalies that might indicate 3I/ATLAS's foreign origins. While claims about truly exotic chemistry remain cautious and under review, early analyses have suggested subtle differences in volatile content, which may reflect its interstellar past or the specific circumstances of its original home system. This step, a careful dissection of the light, did not produce fantastical revelations, but it steadily built a clearer portrait of 3I/ATLAS's nature. In planetary science, extraordinary claims demand extraordinary evidence, and each archived observation became a point of reference as astronomers grounded their interpretations in what could be measured, not merely inferred. Together, TESS's timeline, ATLAS's detection, and Webb's detailed chemistry built a layered understanding. Each method, imaging, tracking, and spectral analysis added a dimension to the unfolding event. Echoes in the archive. The weeks following Webb's observations saw the astronomical world turning back to every available record. Hubble Space Telescope, a workhorse of space imaging, captured its own views, yielding the sharpest images of 3I/ATLAS to that date. These allowed researchers to estimate the size of the comet's nucleus more accurately, analyze its shape, and observe the structure of its coma and dust. By combining findings from TESS, ATLAS, JWST, and Hubble, scientists began to assemble a comprehensive picture. Motion traced by TESS, official confirmation and ongoing tracking by ATLAS, detailed spectral fingerprints by Webb, and high-resolution imaging by Hubble. Each contributed uniquely, showing how multi-instrument collaborations now define the way we study transient visitors from beyond our solar system. The story is not just about a single breakthrough, but about a growing realization. Data once marginalized as background can transform into the seed for major discoveries. With improved algorithms, artificial intelligence, and expanded searches, the potential for finding more interstellar objects within decades-old observations is real. The pulse of new science. As 3I/ATLAS fades back into the deep sky, the broader significance of its visit becomes evident. The 3 confirmed interstellar objects suggest that such visitors, while rare, may not be unprecedented or as unlikely as once assumed. 3I/ATLAS's retrograde orbit and inclined trajectory provided additional confirmation of its origins, while its activity profile and composition offer critical comparisons to both previous interstellar comets and those forged around the Sun. Questions now focus not merely on a single comet, but on a population. How representative is 3I/ATLAS of its kind? Do retrograde, high-inclination orbits unique to interstellar objects leave distinct footprints? As more objects are catalogued and more archives are searched, patterns may emerge about the kinds of small bodies ejected from other stars and what they can tell us about distant planetary systems. Already, models are being refined using Webb's spectra and Hubble's imaging, exploring how different ices respond to exposure to a new star's heat after untold years in frigid isolation. Each new data point informs not just our understanding of 3I/ATLAS, but foundational ideas about how planetary systems evolve, lose mass, and exchange matter across galactic distances. Interstellar visitors, once entirely theoretical, are now a topic rooted in observation. But the lesson from TESS and from 3I/ATLAS's early detection is that our biggest challenge may be in recognizing and interpreting what our instruments have long since recorded, rather than in capturing ever fainter signals. The comet's secrets. At the heart of 3I/ATLAS's story lies the search for composition and soft clues to its origin. Measurements from Webb hint at complex chemical signatures and volatiles, reflecting a heritage not quite like solar comets, but not wholly alien either. Hubble's high-resolution views caricature a nucleus with subtle elongation, active outflows, and structural features pointing to a dynamic evolution through its solar approach. The combination of data means researchers can test theories about how interstellar comets form, how they survive, and what they carry from their original systems. Each detection of activity, each spectral line becomes a tracer, an indirect memory of the system that launched it. And because TESS captured the earliest phase of activity, these initial frames provide rare insight into the conditions under which outgassing begins for an interstellar visitor. Though it is tempting to speculate, Could some ancient pre-telescopic sightings of mysterious tailed stars have been visits from such objects? Current records can only confirm what our technology allows today. The shift is from speculation to observation, aided by our increasing technical ability to monitor, search, and interpret the evolving sky. The price of not knowing. This episode highlights a vital scientific lesson. Revolutionary discoveries often hide in unexamined data. If no one had returned to analyze the TESS archives after 3I/Atlas's orbital path was known, the timeline of its early brightness and activity would have been lost. The comet's history would have started in July, erasing vital context about when and how its awakening began. This humility, recognizing that what we dismiss as background noise may be the signal of tomorrow's discovery, needs to be embedded within the culture of science. Every byte, every archived image holds the potential for reinterpretation. It is a call to continue refining our analytic methods, not just to ask, what is there, but what have we missed? As astronomers reflect on TESS's unintended role, it becomes clear the tools we build for one purpose may unexpectedly solve mysteries we hadn't yet imagined. A new kind of watchfulness. The case of 3I/ATLAS lends new urgency to archive mining, data sharing, and algorithmic searching. With more space missions, planet hunters, supernova trackers, surveys mapping millions of asteroids, each gathering terabytes of images and time series, the next interstellar visitor may already be digitally preserved, awaiting rediscovery. Scientific progress now demands a dual engagement: the eye for new signals and the discipline to reinvestigate the past. The story of 3I/ATLAS's arrival, early activity, and incremental public revelation is a testament to both. It broadens the idea of discovery into an evolving process rather than a single flash of recognition. The search for the unknown relies not just on vision, but on memory, the willingness to question our own records, reinvent the context, and search again. It is a challenge to the boundaries of what we call discovered, and to the patience of those who would look twice. When the sky answers back. For all its cosmic distance, the message of 3I/ATLAS is immediate. In the interleaving of silent archives, delayed recognition, and finally, public discovery, it offers a portrait not only of one interstellar object, but of humanity's evolving approach to the unknown. We are reminded that the universe is neither static nor unvarying, but alive with events both old and new, each revealing itself according to our ability to observe and interpret. With every new instrument, every collaborative network, and every reconsidered archive, we raise our chances of encountering what would have gone unnoticed, of turning incidental pixels into the evidence of a greater shared story. And this, perhaps, is the greatest transformation. The act of discovery has expanded from the present into the past and future, demanding that scientists remain vigilant, receptive, and ever ready for the surprise that awaits within ordinary data. So, where are we left? With a comet, its secrets unfolding gradually, its path illuminated not by a single telescope, but by the layered work of many, and with a charge to memory and imagination. Let us not presuppose that the next breakthrough will announce itself with drama. Often, it will sit silently within the data, waiting for the right set of eyes, the right question, the next chapter in curiosity. Stay curious. The universe is always more than what we see today. and the next great visitor may already be here, written quietly into digital memory, awaiting discovery.